evening, everyone. Welcome back to NPTEL live session. So today is our last session for physics, and after that, you guys should be having an exam. So we will be covering all the topics which are being left out, and we will see some problems. And since this is the last session, I would expect that if you have any queries, questions, you're finding any difficulty in solving the problems, please let me know so that I can help you to get your doubts clear and you will be feeling great in giving the exam. So shortly we'll start the session. Hope to have your questions. Okay, so since we have talked about many catalysts so far for which have been used for polymerization, specifically for ethylene and propylene, today we will be looking at some other metal-based homogeneous catalyst systems. So let's start with the lanthanide-based homogeneous catalyst. So similarly, the way we have seen the CP complexes, here also we have a cyclopentadienyl thing with methyl groups and substituents. And here you have a location. The other ring, the same methyl substituents, and it is connected with methyl and old. So when this catalyst is being used for ethylene polymerization, so n number of moles of ethylene molecules we have used, this process is quite fast. To give you, if I'll write the CP star as sitting, so this is the notation of CP star. So I'm writing in a shorter form CP star, which gives you the same meaning. And since this is getting polymerized, so one after first insertion, it would form the polymer. So this is the fast reaction. Similarly, if the same catalyst we are using, the lanthanide-based catalyst, and we are trying to polymerize propylene, this reaction is also very fast. So it will give you the first, we are not writing the N over here, it's the first propylene group that will give you viscosity. After that, when we are adding second propylene, this process becomes slower and it ends up in a dimerization process. So dimerization happens at this ends at this step itself. So it will not further propagate. So this is your does not proceed further. So only a dimerization we could get. So to analyze why this kind of behavior we are getting when we were using the zirconium-based catalyst, which we have seen in last two lectures, but there we could have the polypropylene as a product, but here we are only getting the dimer as a product. So why is it happening? So if we are taking an isostructural species where I am writing a notation and with R butadiene group. So this is just the ligand system we are talking about, and here we are talking about the zircon. So earlier we have seen the things with the zirconium. So what is the difference? This is actually, if you see the complex, this was a charged complex, and this is a neutral complex. They both are isostructural, but isoelectronic species. Number of electrons are same. So both are isoelectronic, but still there is a difference. And DFT calculations, they suggest that even though even though we are taking instead of this zirconium, we are taking this lanthanide-based system, their isoelectronic species are different. They are not same. So one is neutral, one is charged, and the zirconium one that favors polypropylene formation, whereas the lanthanum one that favors only dimerization. So there is a difference in product formation, in the selectivity, because it is neutral and that is charged. So that is where we can use it, but it will give you only up to dimer drop. Also, one important point that has been seen that in case of lanthanum-based alkyl compounds which are having the CP groups, it has been seen that sigma bond metathesis reactions are happening. So they are reported. So here the metal can be scandium, it can be yttrium, it can be lanthanum. So we are starting with, we are taking only M, the CP star group, and here the methyl group. So as we are saying that sigma bond metathesis can happen. So in presence of propylene group, what would be the expected product? Since that sigma bond metathesis is happening, so we are taking here metal CP star, and here your propylene group. Now it will give you out the CH3 group on having your propylene group. This is because of the sigma bond metathesis reaction. You will ended up having double bonded. These complexes here it is having a metal alkyl group and they are found to undergo sigma bond metathesis when treated with propylene group. But yet there is no application being found. That's a drawback over here. Moving from this lanthanum base, we are going towards the iron age of polymerization, where iron has ruled in carrying out the polymerization of ethylene and propyl molecule. So one such structure that we have in hand is it's generally a pincer system where nitrogen based pincer system should be there. So if you have a pyridine molecule and it's a double bond N, and this nitrogen is charged with R dash R, R dash R, and the other two sides pentacoordinated and here. And we are using a methyl aluminum oxide as a reagent, which is more than 300 equivalents. So there are two conditions. If we have with the same complex, if we have R equals to methyl and R dash equals to proton, so then we will be ending up when we are treating it with N times of ethylene, we will be ending up having this product, which is an oligomer, alpha olefin kind of structure, and with a chain C10 to C20. Okay. And here, if we are having R equals to R dash, which is equals to methyl only, then it would give you a high density linear polymer polyethylene. So this is the difference when we have a different substituents altogether. Now, moving towards, if you are taking We are trying to understand the chain growth, how this particular system grows. So we will take the general procedure. Firstly, I am considering that whole ligand as NNN. Fe as a positive charge, and we already have one particular ethylene molecule inserted, so it's a polymer. So there is one possibility of treating with ethylene, and it can undergo, since it is having, this is alpha, this is beta, and this is beta hydrogen. So this beta hydride could eliminate, and therefore you will be ending up having NNN, Fe positive, H, and this is again, so we will get a chain growth, right? The next possibility that we have is, if you are using trimethyl aluminum or MaO, then what it would form, it would react with the methyl of aluminum, and it would give you a polymeric chain with AlMe2 plus releasing NNN, Fe positive, having a bond with methyl. Then this reacts with your ethylene, again it gives you a chain insertion and coordination. The third one that we have is, third possibility, that if we are having this N, 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 Fe positive hydride, and polymeric chain, then the ethylene molecule comes in, the propylene goes out. So this is called an associative exchange, where N, N, and N, iron, hydride, this would become low because ethylene is going to connect over here. Again, this would give you a chain growth of polyethylene formation. So there are three possibilities and how it propagates when we have a methyl aluminum oxide, or if we are undergoing beta hydrogen elimination, or if it is undergoing associative exchange. Now, moving from iron catalyst to nickel-based homogeneous catalyst. We should not forget that polymerization has been initiated with the nickel-based heterogeneous systems, that is the nickel effect, and after that, Gibbs-Renata catalyst came into picture. So here we are talking about the nickel-based homogeneous catalyst. So generally, in this particular case, we use ligand of such type, bit big, bulky nature, same group here. Or you can have nitrogen double bonded nitro double bonded N. Right? So we are calling them as N. This curve represents the whole molecule. We can't draw it again and again. So just for just the symbolization. Now we have this ligand connected with your nickel. Generally, it would be in square planar shape. with the methyl, two other substituents as methyl, in presence of diethyl ethyl minus 78 degrees Celsius, very low temperature, and OET, PAR4 meter. This is a proton source. Methyl can take up H positive and can go as methane. And what it will form? It will form your N, this is nickel, one methyl, and the other group has OET, solvent molecule. So after that, this is the counter ion. When we are treating it with alkene, so it will form CH2, CH2, X, CH3, and this propagates. So this is your polypropylene, which is highly branched. So this is one such method when we are using a proton source and followed by the methane law, it will give you polypropylene, which is highly branched. The second pathway that we have is, so this is your first pathway. The second pathway is, now we are starting with the bromide system instead of the cell system, and we are using a MAO methylating agent with 1000 equivalents compared to that one in toluene medium, and substrate are propylene, where R we can expect to be proton or methyl or butyl, etc. So it will also form CH2. So what we will get from here is high grade linear polymer. So there we were getting the branch polymer, there we will get a linear polymer. So based on the different reagents that we are using in starting complex, you will end up having different properties of your polypropylene. Now there is one more example which has used a combination of nickel catalyst and the titanium catalyst in a tandem reaction. So together they have been used. So we have a three-way system. Okay, so there is one row. Here one formation nickel, oxygen. Here nickel is coordinating with your and this is C6F5, just a charged molecule. So here we are introducing the ethylene molecule. It is taking out this group, then followed by ethylene using the titanium based system. We have already seen in our previous reactions. And what we will end up having is your this product, which will generate the low density linear polyethylene. So here the two catalysts, titanium and nickel based, they have worked in tandem in same medium with one substrate that is clean to give LLTP, low linear low density polyethylene. So it's a combination of two catalysts that we have seen here. So let's take a look at the summary that we have each of ours. So we actually started with nickel catalyst, and this was an accidentally found nickel effect. Then we did it deliberately to introduce the Ziegler-Natta catalyst, so which was heterogeneous in nature, followed by we went to zirconium and titanium based metallocene catalysts, which are homogeneous in nature. Then we have just seen the lanthanum based metallocene catalysts, which are also homogeneous and they belong to non-group 4 metals. Followed by we have just seen iron, which is having a non-CP ligand. And again, we went to the nickel homogeneous phase catalyst. So this is the summary of what kind of catalyst we have used for the polymerization, either of the ethylene or propylene. Now there are certain co-polymerization reactions also. Say for example, we are taking ethylene molecule and we are trying to co-polymerize it with this group. So the catalyst that we are going to use is platinum-based catalyst. With having OEP and methyl substitutions positively charged with BAR4 negative. The conditions for it is happened in DCM 1 to 6 bar of pressure and 30 degrees Celsius. So the product that we are having is CH, CH2, OR. So there is this ester chain CH2, I, CH, same group here, CH3, CH2. And this is an amorphous material which is highly branched product and having polar ester side groups. So this is happening after your co-polymerization. Then we have to do the co-polymerization with of ethylene with the carbon monoxide C2H4 with U. So 1952 Pepe has given this presence of the catalyst. So we will end up having this product, which is poly 3-oxo 5-methyl. Whereas later, if we use ethylene with NCO in presence of phosphine group, palladium catalyst, proton probe, ethanol, divided these, and 40 bar will give you ketone with the number as 20,000, melting point as 260 degrees, and it's thermoplastic in nature. So these are just the properties when we are using different catalysts, different conditions for co-polymerization between carbon monoxide and ketone. So what is the mechanism of this one? So we have the phosphine group, palladium. Firstly, there would be loss of acetate groups and it would form the others giving a sign of a curve. After reaction with carbon monoxide, monoxide will bind to your palladium and then ethanol it will release the proton and will form proton coordination with a positive charge. And after treating with so we will have this step where when we are treating with ethylene and carbon monoxide, so it will give us so this is having alternating ester has an N group in polymer, right? So how the chain propagation step happens? We have this palladium. This is a polymer. Now we have to do the propagation. So this way come and insert over here. Everyone will. Now the second will come as ethylene molecule. And again carbon monoxide, palladium. So you can see that we have an ester ketone, then carbon C double bond O, then ethylene group, then C double bond O, then ethylene group and a polymer. So this is actually the propagation. So it will ultimately will give you poly oxo trimethyl. So this is the way it goes like an alternating thing. So ultimately we can, and besides this, there are many biological organometallic based catalysts also. For example, vitamin B12, cobalt complex, which are used in biology, which I've seen many applications in biology. So here we are summarizing of what we have read in this particular session. So we were talking earlier, we started with early transition metals, catalyst, and late transition metals. So if I would say that what was the central metal, so it was having titanium in plus 4 state, it was having zirconium in plus 4 state, hafnium plus 4, and lanthanum in plus 3. Whereas late transition metals are one which are having iron in plus 2, nickel in plus 2, palladium in plus 2. Now the second feature, that is the ligand. So generally here the ligand is CP and halide. Here it is diphosphines, diamines, and sometimes halides also. The third factor that we have is the counter anion. So the counter anion in this case is non-coordinating. We have not seen the counter anion coordinating with your system, whereas here it is weakly or non-coordinating. The fourth one that we have is the coordination geometry. So they have been generally found to be pseudo octahedral, whereas these are mostly quadlinear, followed by the active site. So here the active site is, so here the active site is metal with CP groups and a polymeric group over here, and here is a vacant site with a positive charge. And here also, instead of the CP, there would be any other ligand, L and L. And the last pointers. So does these catalysts have functional group tolerance? It means in presence of other functional groups, they will not show any activity. So it does not have functional group tolerance, whereas this one is having functional group tolerance. So this is what we have read in these lectures today. I hope you have understood it well. If not, please feel free to ask the question. We'll wait a few minutes to start the problems. So if there is no question, we can start the assignment. So it's also very straightforward. The substrate to the following transformation, we have already seen that what would be the substrate that it would give you a linear chain. So it's clear there is no in presence of the lutetium methyl complex. It is known for the polyethylene formation, and it's a polyethylene only. The substrate has to be ethylene for ethylene polymerization that gives its iron catalyst with comparable activity to the Zitner catalysis, which we have already seen. Which iron complex has been seen to give that kind of activity, so which is having this NN system with the halide substituents and a almost high coordination number. So this is the one, the substrate of the following transformation. So we are starting with this substrate and we are using this iron complex. What we are getting at the end, that's in oligomer. We have already seen there are what pathways we have selected, and one will give you a C6 to C10, and other one will give you a longer chain. So this has happened with your ethylene molecule. So we have seen with MAO when we are using a methyl aluminum oxide, and where if you see properly that your R groups that we were talking about earlier, if they are methyl and R dash is your, this is your R dash, which is hydrogen. Here also R dash is hydrogen. So when this is a scenario, we end up having the C6 to C16, and this only possible with the ethylene. We have seen a mechanism also. Oxidation state of the cobaltine coenzyme is B12. This is what I was talking about, the bioinorganic catalyst. So it is generally in +3 oxidation state. The examples of bioorganometallic compounds is your B vitamin B12. That is your involving bioorganic compound like C cobalt is there. So there is something which is aqua cobaltine where the coordination is with water, and its other name is vitamin B12R. And the last thing is like in MRI, what are the agents that we use? So generally we use the gadolinium kind of complex. So option C is right. So with that, our session is over. If you have any questions regarding the lectures that we have done so far, any topic, please feel free to ask your question or put your question in the chat box. I'll be happy to answer.